So we're Kick Brass, the ammunition casing sorter. This is our final design presentation. Team 7, we're Brent Einstein, Kyle Hughes, Mason Megahan, Adam Powers, and Molly Rhodes. So a quick overview of our project and the presentation we have today. We're going to go over what we did in the first semester of the course, including the problem definition, things like the concept generation, our decision-making process we used, the engineering analysis that we did on the initial setup, our fabrication of the prototype, which we did in the beginning of the first, or the end of the first semester. We have some testing and results that we started in the second semester, a quick budget analysis to see where we are on money-wise, and then the entire project timeline from beginning to end, some future modifications we could make to the system, as well as our conclusions and our references. So, although many people who reload at home, including myself, have a real pain when it comes to sorting cases. And so our team decided that we wanted to make a small at-home case sorter that would take care of all the long, tedious hours of sorting through your ammunition cases. So what we decided to do was to look at what is currently in the market, and there's two main things. There's the industrial size ones that are for commercial use, and the problem with them is they're very large and they're extremely expensive on the scale of $5,000 to $10,000. And then other than that, there's just these small trays here where you shake and the brass goes through. The problem with those is they're just cheap and they don't do very well, and then you still have to manually do the work yourself. So in order to get something else in the market, we wanted to design an at-home system that would be automated and would be able to sort through at least 3 different types of cases. So some constraints that we decided to go with, we want the entire unit to weigh less than 30 pounds in order for just the regular human to be able to lift it and work it around it. Obviously the prototype would need to be less than $500 as it's our budget for the Capstone project. We also wanted to be able to set the system, leave it, have it do its work, and then come back to your sorted cases. So we don't want to have to do any human input once it's started. We also wanted to go from cases that are 380 ACP up to 50, so 0.38 inches to half an inch in case dimensions. And then we also wanted to make sure that none of the casings are damaged in the process, or at least a very small amount of damage. And so some objectives we have, obviously we want the sorter to case, or sorter to sort the cases effectively and accurately. It's going to be pretty worthless if it can't do that. We also want the case sorter to be inexpensive so that the average home reloader can afford it, pretty much just on the same general basis as other reloading equipment is. We also want the system to sort multiple types of cases, as I mentioned previously, from the size range. We also want a couple different in that size range. And then we also wanted to make sure that our design is compact. We'll pretty much determine and make sure that this is something that could be set up on a bench top or similar area. And then we also wanted to make sure that the entire system can sort quickly and do this effectively.
So here's our quality function deployment, QFD. It outlines our engineering requirements and our customer requirements, as well as engineering targets and our benchmarks. For our benchmarks, we had the CDS and shell sorter. Those were the current existing case sorters that Brent talked about previously. The engineering requirements are metal thickness, weight, rate of error, cost, and size. Our customer requirements are inexpensive, looks nice, sorts accurately, lasts a long time. It's a compact system and it's durable. Within the QFD, it shows the relationships between all of these criteria. The House of Quality shows the criteria from the engineering requirements on the previous slide of metal thickness, weight, rate of error, cost, and size. All of these criteria had direct relationships indicated by the plus signs. There were no inverse relationships as would have been indicated by minus signs. So we use the house of quality to determine what the best design would be. So during the concept generation and decision making process of our project, we came up with this functional diagram. Here on the bottom right hand corner we have the legend, which indicates a green arrow for electrical components and an orange arrow for mechanical components. We only had one electrical component, which was from the controller to the motor, and the rest were mechanical components, from the motor to the vibratory bowl, the feeder copper, and then from there to the rail system or sorter, and again from there to the boxes or the collector. And we came up with our critical component being the sorter. We came up with that because the most important part is the sorter. If the sorter doesn't work, then our whole system is completely useless. And so the purpose of this kick brass ammunition case sorter is to sort the cases. So at the end of the first semester, we tested our critical component, and it ended up working. So and we'll get to that later. But continuing on with the decision-making process, here is our criteria for evaluating our different designs that we came up with. The criteria on the left are cost, capacity, size, feed rate, and weight. As you can see, the different relationships between those criteria. We use these to determine the optimal design of the 20 or so designs that we had come up with. The weights on the right-hand side are in that respective order, about 12%, 25%, 22%, 27%, and 14%. And this is the final CAD model of our ammunition case sorting system. The feeder bowl is the main bulk of the system. The transition piece is there on the left-hand side, and on the outer rim we have the sorting track. And this was the design that best suited our applications for the ammunition case sorter.
So in order to make sure that our design was appropriate for the application that we wanted, we did some engineering analysis, and so we imported the CAD model from the previous slide into ANSYS, and we did a static structural because our component is not undergoing any kind of heat transfer or anything, so we decided that a static structural analysis type would be the most appropriate. So the way we set this up was we had a fixed support on the bottom of the bowl because that's going to be attached to the tumbler, which is going to cause it to vibrate. And then we also added a fixed support to the end of the rail system because ideally that will be bolted onto the feeder bowl itself. And then we applied a load of 55 pounds to the bottom of the feeder. And then on the interior track of the feeder, we applied a load of 10 pounds. And on this rail, on the sorter, we applied a load of 3 pounds. And this is very much for a worst case scenario. Casings don't actually weigh that much. Ideally, the weight in the bottom of the feeder would probably be more around 5 to 10 pounds in reality. But we wanted to do an analysis for the worst case to make sure that the system will never fail structurally. So this figure shows the total deformation on the whole structure. And as you can see, the maximum deformation is 0.18 inches, roughly. So we figured that that's not much deflection at all. And again, this is for a worst case scenario. So we knew that the structure would be safe from a deformation standpoint. This slide also shows the von Mises stress on the structure, and the maximum stress is 687.39 pounds per square inch, and the maximum stress occurs in that transition piece because in the model we didn't have any kind of support on it, but in reality it was supported better when we actually created the model. But this was just, again, for a worst case scenario, this is what the stress on the structure would be. And then because our structure was vibrating, we wanted to do a modal analysis to figure out what the resonant frequencies of the structure would be, because we didn't want it to fail because if we were vibrating it at the modal frequency, because that would be very bad. So here in this table, we have the different modes and their corresponding frequencies. The actual structure, the tumbler operated at 60 hertz. So we're kind of in between mode 7 and 8, but we never actually hit those frequencies in testing, which we will talk about later, more about testing. But our structure was pretty much safe from an engineering analysis standpoint. So we knew we were safe to continue with producing the structure as designed. And so we began prototyping, and here are some shots of the fabrication process. So in order to mount the tumbler, or the feeder onto the tumbler, we 3D printed that blue plate, and that just allowed us to fix the feeder bowl to the actual tumbler. It made it easier to get a nice level surface to attach the feeder with. So that was 3D printed. And then also we 3D printed the feeder bowl, and here we are drilling the holes so we could bolt it onto the tumbler. And everything was 3D printed because machining it would be entirely too complicated for what we had the ability to do. And in the FEA, we ran it with PLA material properties. And so those were the pictures that were shown in the previous slides. And we saw that there was minimal deformation, so we knew we were safe to just go ahead and 3D print all components. And here are some more pictures of the prototyping process. So we showed the bottom view and showing how that blue plate fit onto the feeder itself, and then that would all get mounted onto the tumbler. And in this figure, we show the final assembly, which shows the transition piece and the sorter attached to the tumbler. Those just got glued on, and then we bolted the sorter onto the feeder itself.
So once we finished the assembly of the whole sorter system, we could continue on with actually testing the system and seeing how the feeder worked. As we already mentioned, the critical component of our system was the sorter. And we already tested that last semester and showed that it worked. So at this point, it was our feeder that we really wanted to ensure worked well. This is a video here that will show the initial testing process when we put cases in just to see how the feeder would work. So you can see in the video here that the cases are moving a little bit, but what we saw is they're going in the opposite direction of what we really needed for them to go up the ramp. So we could see that there was vibration here, it just wasn't what we needed for the feeder system to work. So what we decided from this is that it's really just the vibration platform is causing too much amplitude in the vibration, causing the cases to jump around too much, while maintaining that frequency that we need. So as a fix to that, what we needed to do was decrease the amplitude and maintain the same frequency, and hopefully that would be an option. We talked about a few different ways to actually remedy this problem. One was coming up with a different vibratory base that was based on electromagnets that they use in industrial settings. Another run was just to go with a simpler feeder design altogether, still with vibration, but instead of having to move up a ramp, to use gravity to pull the cases down in a vibrating action just to oscillate and help them move. The third option that we came up with was in respect to the counterweight on the motor. The way the motor works is that there's actually a counterweight that is offset on the shaft. That causes the vibration action. So you can see on this slide here, this is the actual counterweight that we had on here. We 3D printed this just like we did everything else, and it has a set screw that we can just apply to the shaft of the motor and put weights in it. We incrementally increased weights in that until we got a vibration action that seemed to work a little bit better. So in this here, this is our final, actually the system working after we made those changes to the counterweight. And you can see that the cases are moving now in the direction that we wanted to. They were going up the ramp, and they were going down the sorter system. At this point, we had two different cases in there. We had 9mm and we had 40 cases. And it does show that they actually sort in the correct things. So we had a 100% success rate on what they were sorting. The system was just slow. So that's kind of what we talked about, is how are we gonna get this to go a little faster? We discussed maybe the orientation of the cases being all flat to start with and all standing to start with, to see if those made a difference. So I'll move on to the next slide here so you can see this. This is the test with all the cases laying flat originally. And what is noticeable from this video is you can see at the start of the ramp there's a case that actually gets stuck on the side of the ramp. And that really kind of led us to the conclusion that maybe that's what's causing the cases not to move so fast. So that could have been one of our problems. And in future testing, we'll talk about it, but that could be an issue that we need to address. We did another test where we had all the cases standing up. The problem with that is just the vibration. It was enough amplitude to make them all fall down. So it really just ended up in the same scenario that we had in the first two slides. But we did see from the cases all flat scenario that we could make changes to it and hopefully get it to run a little quicker.
So this slide here shows our budget analysis. Up to this point, we've spent $134.42. Most of that was the actual tumbler base that we had to purchase. Also the filament for all the 3D printing that we talked about doing. And that filament, we had purchased enough where we were actually able to use that same filament to print the extra pieces that we talked about, the transition piece as well as the counterweight, the new counterweight assembly. So we're definitely well within where we needed to be as far as our budget of $500. So to recap how we got here, we started, this is the first semester's project timeline. We started with problem generation and project planning, which you can see the highlighted bold there, headings. That's the first heading. And then we moved into concept generation, which we developed a concept of how we would fix the problem, which in the last heading we would have defined the problem. Moving forward from there, we moved into decision making, which is how we would determine whether or not our solution could fix the problem and how well it would do that. Moving from there, we selected the concept by using the previous section's weighted ratios for that specific problem and how each possible concept would address the problem. And then we did as we saw in the previous slides, we did the engineering analysis of the components to determine that our design would actually work engineering-wise, whether it would be safe and whether it would be able to handle what we were doing. And then as I said, this is the first semester, so last semester we were able to prepare a final presentation and report in which we documented that critical component and showed that our critical component for that portion was the sorter itself, and we were able to show that that did indeed work. For the second semester, we did multiple design reviews, which you can see in the bold headings here. We have design review 1, 2, 3, and then our design review 4, or our final design review. The first heading there, we have the introduction for the second semester, in which we went through and we introduced what we were going to do for the second half of the project and how we were going to make it to our final demonstration. For the second heading there, we have the fabrication, in which we looked into how we're going to fabricate it, and we actually began fabrication on the project itself. For us, we actually, on the third heading, when we went into testing results, we ended up further doing some more fabrication, because whenever we initially tested it, we found issues, and that's essentially what this stage is for, is you test it, you find your results, and then you determine what we can do to move forward and make the final project better for the demonstration. And then for the final design review, that is where we are now, where we have tested the entire project. We've tested it and we've demonstrated that it does indeed work and that it is a viable concept. For future modifications for the project, we would look to optimize the mass on the counterweight to make the casings move faster, if faster is what we need. Now that is something else in the future that we would look at, whether they need to move faster or whether it is a vibration issue. If it was a vibration issue, then we could possibly use a vibratory feeder base instead of the tumbler, so we can have more control over the direction of the vibration and the amplitude as well. Also, we could look at integrating a controller into the system that works with brushless type motors, because that's one of the issues we had, was our controller that we did purchase was not specifically compatible with brushless type motors. And we'd also need to determine a way to decrease the noise of the system. So to wrap it up, kick brass case sorter solves the defined problem which we talked about. Our initial design does meet the constraints and objectives with little modification, the main modification being the counterweight. The counterweight modification did prove successful to remedy the initial testing problems that we did find. Optimizing the system would require further testing and further analysis of the vibratory base, as which I just spoke of, whether that would mean testing it with different counterweight weights or simply finding a different vibratory base, maybe an electromagnetic one as we spoke of. And finally, the next critical step for making this project an at-home application would be finding a way to dampen the noise that comes off the product, because that is the biggest thing that would, at this point, separate this from being in like a big like corporation room where they would have sound dampening on the room itself. For an at-home application, you would have to figure out how to make the device itself quieter. There's some references. Thank you.